Good morning, afternoon, evening. Welcome to today's lecture on the structure of atoms. In this lecture, we'll delve into the intricate details of atomic structure, exploring the historical and modern perspectives that have shaped our current understanding. We will discuss atomic theory, the Bohr model, ionization processes, the significance and organization of the periodic table, and the concept of isotopes. We aim to provide a comprehensive understanding of these topics with relevant mathematical examples where appropriate. Atomic structure: atoms are the fundamental building blocks of matter, each consisting of a nucleus composed of protons and neutrons and surrounded by a cloud of electrons. The atomic number, defined by the number of protons in the nucleus, distinguishes one element from another. For example, sodium atoms have 11 protons, while copper atoms have 29. Most of an atom's mass resides in its nucleus. Despite the fact that the nucleus occupies a very small volume of the atom, over 99.9994% of an atom's mass is concentrated here. Thus, the atom can be visualized as mostly empty space, with negatively charged electrons in this space anchored to a positive nucleus by electromagnetic forces. Historically, the idea of atoms dates back to ancient philosophy. The term atom originates from the Greek word atomos, meaning uncuttable. Modern atomic theory took hold in the 19th century largely due to John Dalton's work, who provided empirical evidence that matter is composed of atoms. Bohr model of the atom: the Bohr model, introduced by Niels Bohr, was the first quantum model to successfully explain the spectral lines of hydrogen, paving the way for modern quantum mechanics. Bohr conceptualized the atom as resembling a mini-solar system, with electrons orbiting a dense nucleus. This planetary model utilized electrostatic forces for attraction, unlike gravity in the solar system. The Bohr model posited that electron energies are quantized and electrons could only occupy certain discrete energy levels. This addressed problems in earlier models, such as the classical idea that accelerating charges orbiting electrons would continuously emit radiation and thus collapse into the nucleus. Instead, electrons do not lose energy while in a stable orbit due to quantization. For hydrogen, the energy levels are described by the formula En equals -13.6 Fn, where n is the principal quantum number indicating the energy level. Ionization energy: ionization energy is an essential concept that quantifies the energy required to remove the most loosely bound electron from an atom, ion, or molecule in its gaseous state. The first ionization energy is often expressed as Xg plus energy Xg plus E, where X represents any atom or molecule, and X represents the resulting ion. Ionization increases across a period in the periodic table as nuclear charge increases, and decreases down a group due to shielding by inner electrons. Several factors affect ionization energy, including electron configuration, nuclear charge, and electron shielding. For example, elements with a full valence shell have high ionization energies due to their stability. Periodic table developed by Dmitry Mendeleev in 1869. The periodic table organizes elements by atomic number, reflecting the periodic recurrence of their properties. It classifies elements into rows, or periods, and columns, or groups. Elements within the same group exhibit similar chemical characteristics, while trends such as increasing atomic number are also evident. The table E structure has evolved to reflect advances in atomic theory and remains a pivotal tool in chemistry and related sciences. Isotopes are variations of elements differing in neutron number yet sharing the same number of protons. This variance in neutron number leads to differences in mass and certain physical properties, though all isotopes of an element exhibit similar chemical properties. Isotopes are essential in fields such as radiometric dating and nuclear medicine. For example, carbon has several isotopes, including carbon-12 and carbon-14, the latter being pivotal in radiocarbon dating. In summary, atomic theory and models such as the Bohr model have transformed our understanding of matter. The concepts of ionization and periodic ordering of elements in the periodic table further illuminate the intricate patterns and behaviors at the atomic level. Isotopes add another layer of complexity to this understanding, highlighting the diversity within elements themselves. Thank you for your attention during this lecture. I encourage you to explore these concepts further, as they form the foundation of both theoretical and applied chemical sciences.